want this to be a letter, and you just want to add another letter to it. So when you program, and this is something we'll learn about, you have the concept of variables, and this variable holds, it references some of those binary numbers in memory, and a computer needs to know the context of that. If that string of binary data represents a number.
Trying to sell to me that day in high school, and I was sitting in the back, and I just woke up, and I said, that can't be right. I just had this visceral reaction that said, I can see what the algorithm does, and I know it swaps everything, but it just seems too inefficient. It has this loop that keeps on going, and it's not a for loop, it's a while loop, and it just seemed to me that it was possible that this loop could go forever. Depending on the choice of random numbers, this might never terminate. And that just seemed wrong. It seemed like there was a much better way. And in my head, I came up with the shuffle algorithm that we showed before. Knuth calls it algorithm P for permutation. It just seemed like that was a simple and correct way, and this was just too complicated. And that really bothered me. I thought that an algorithm should be guaranteed to terminate. Now here's the algorithm I was able to come up with. Knuth calls it algorithm P. Other people have discovered it before again, so it's been discovered over and over again. And the idea is you just
Now a dynamic language, on the other hand, every time you run it, all it is text. So it's not like an executable, it's not a binary file. But also, every time you run it, you're running the actual high-level, human-readable, somewhat readable text file, pretty much. And then every time you execute it, there's another program that first it translates into machine language, and then it executes it. And in the case of JavaScript, this is done by a virtual machine. That's one of
that it was exactly 50-50 in my simulation, but with the teacher's algorithm, way off. 1/6 of the time you get a B, and 5/6 of the times you get BA. Now, in this quiz, we're going to consider each of the shuffle routines, that is, the shuffle routine coming from Knuth, the algorithm P, the shuffle 1, that was the teacher's original shuffle, and the shuffle 2 and 3 that we just saw. And for each of them, I want you to tell me, is the runtime order n or order n squared, and is the result that we get back correct in the sense that all outcomes are equally probable? We already know that the shuffle routine is order n, and it is correct, and we know that shuffle 1 is order n squared, and it's not correct. And now what I want you to tell me is, for shuffle 2 and 3, what's the order?
the series web programming step by step, where we're going to learn how to use JavaScript. The first thing I want to do is just explain what JavaScript actually is and what it's used for. And then I will kind of introduce this series and where we're going to go with it. So the first thing, obviously, JavaScript is a programming language, first and foremost. It's most commonly used in websites, and that's why this is part of the web programming course. But a few things about JavaScript that I call on misconceptions. First of all, JavaScript.
So every monad is different from every other monad. Like there are never two beings being perfectly alike. Like these apples you're seeing on every created being, and consequently its monad is subject to change. The change does not occur in a jump, but it occurs continuously. It follows that the natural changes of the monads come from an internal principle, because an external cause can have no influence upon the inner being.
So we knew that we were always impressed that it was very, very important, and speed was the essence.
enters in the random index position in the array. So the last line we need to complete that, we target the index position in the loop passing, and we put the temp value within that. So basically what these three lines do, it does the swapping of the two values into the two index positions they need to go in. So if we take that and we run this in our favorite browser software, you can see we get a shuffled array. And each time we refresh, each time that little application runs, it gets a different shuffle. And the Fisher-Yates modern shuffle algorithm is supposed to result in an unbiased, efficient shuffle because you're mixing the array, the original array, into itself. Now, we want to have something that's a little more reusable and useful, so what we'll do is we'll add this to the array object as a method. So we'll type in array.prototype dot the name of the method that you want. We'll name this shuffle is equal to behind the Fisher-Yates modern shuffle algorithm. Now what we'll do is open up our favorite code editor and we'll program this in JavaScript, and I'll show you how it looks in JavaScript. First, establish a new example.html file. And in it, we're going to open up a script element, make sure we close it, and let's establish our array. And this array is going to have 8 elements within it. The first element is an A, that's at index position 0. Index position 1, we're going to have a B, all the way through H. Now the next thing we do is create some variables that our loop is going to require. The first one is going to be named I, and that's going to be equal to our arrays.length. Then we can put a comma, and the next variable we're going to establish is J, and that's going to represent our random number that we generate with the loop each time the loop passes. The next variable is temp, and that variable is going to hold the temporary value so we can do some swapping between the two indexes and
for characters or whatever it is. And in most static languages, every variable has a defined type, so the computer knows how to interpret the data that it uses. And in JavaScript, that is dynamic, meaning at one time you can have a variable that holds a number, and then it can all of a sudden hold a string and other more complex subjects. And we'll talk more about variables and numbers and strings and stuff like that as we go on. But I just wanted to talk about that in this first video. The other misconception about JavaScript is that it is, although it is most commonly used in websites, it is not only used in websites. Every browser, like Google Chrome or Firefox, Internet Explorer, they all have a JavaScript virtual machine.
behind the Fisher-Yates modern shuffle algorithm. Now what we'll do is open up our favorite code editor and we'll program this in JavaScript, and I'll show you how it looks in JavaScript. First, establish a new example.html file. And in it, we're going to open up a script element, make sure we close it, and let's establish our array. And this array is going to have 8 elements within it. The first element is an A, that's at index position 0. Index position 1, we're going to have a B, all the way through H. Now the next thing we do is create some variables that our loop is going to require. The first one is going to be named I, and that's going to be equal to our arrays.length. Then we can put a comma, and the next variable we're going to establish is J, and that's going to represent our random number that we generate with the loop each time the loop passes. The next variable is temp. And that variable is going to hold the temporary value so we can do some swapping between the two indexes. And
or characters or whatever it is. And in most static languages, every variable has a defined type, so the computer knows how to interpret the data that it uses. And in JavaScript, that is dynamic, meaning at one time you can have a variable that holds a number, and then it can all of a sudden hold a string and other more complex objects. And we'll talk more about variables and numbers and strings and stuff like that as we go on. But I just wanted to talk about that in this first video. The other misconception about JavaScript is that it is, although it is most commonly used in websites, it is not only used in websites. Every browser, like Google Chrome or Firefox, Internet Explorer, they all have a JavaScript virtual machine.
But in computer science, we usually use binary trees, which means that it consists of nodes where you have a root node, and then every node can have a left child and or a right child or neither. In fact, the root doesn't have to be there either. But anyway, so in binary trees you have left and right. But the ternary trees you have left, middle, and right. So here's an example ternary tree where the root has a middle child and a right child, but no left child. And then here the right child in turn has a left child, but no middle. And this guy has left and right.
Chance. What do you think? Yes, they're all the same, it just takes longer to get them. No, some of them will be different, have a different probability. Or no, some will have a zero probability, that there will be some permutations that it's impossible for the teacher shuffle to generate. Tell me what you think. And this is a hard question. It takes some analysis to be able to figure it out. You may be able to tell just by looking at the algorithm, or you may want to write some code to analyze what the situation is. And the answer is that every permutation has a non-zero probability, but they don't all have the same probability. Now let's see how I discovered that. So I wrote some test code that generated this output, and what I did is I gave it some example inputs, some example decks that were very simple. First I gave it the deck consisting of 3 items, A, B, and C, and then I gave it the deck consisting of 2 items, A and B. And I had it test for both shuffle algorithms, the correct algorithm and the teacher's algorithm.
In the next pass of our loop, we're going to be affecting index position 2 of the array. Then we generate a random number between 0 and 2. Let's say that happens to be a 0. And we take index position 0 and we swap it for index position 2. And in the final pass of the loop, we're going to affect index position 1. And we generate a random number in between 0 and 1. So let's say it happens to be a 0, and we take the value found at index position 0 and we swap it for the value found at index position 1. And that's how it works. Each time that you do it, it'll be different because different random numbers will be generated each time. And that's the logic.
All the items have been swapped at least once. So it looks like this. Again, we have this deck of cards, and then we have a parallel array of the same length, which tells us whether we've been swapped or not, and that starts out as being all false, while this one starts out being cards. And then we go through and we pick out random numbers. So say we pick out I and J as being here and here, and say we have a 9 of diamonds there, then we're going to just swap the two. And so we cross those out. We now have 7 of spades there, and the 9 of diamonds there, and we mark the two spots as being swapped. So now this one's true, and this one's true. Those two spots have been swapped, and then we keep on going until all the elements swapped are all equal to true, then we know we're done. So that's what my teacher was trying.
So we knew that we were always impressed that it was very, very important, and speed was the essence.